Hello everyone and welcome to our third lecture. Today we'll learn about two fundamental components of the theory of programming languages, which is lexical analysis and syntax analysis. These two steps are part of the compilation process and serve as the foundation for understanding how programming languages are structured and interpreted. So, we'll explore their definitions, processes, and significance in computer science, and you'll have a clear understanding of how programming code transforms from text into executable instructions. Okay, so let's begin by outlining the objectives of today's lecture. So, we'll understand the concepts of lexical analysis and syntax analysis. So, we'll break down these critical phases of the compilation process to show how they contribute to transforming code into executable programs. Then we'll learn the phases of a compiler that deal with lexical and syntax analysis. Then we'll try to understand the tools and techniques used in lexical and syntax analysis. Then we'll work through examples and code snippets for clarity. Okay, to understand the theory of programming languages, we first need to look at the overall compilation process. So, the compilation is the process of converting high level source code into machine code that a computer can execute. So, when you will write a code, you have to compile the code so that it convert that high level source code into machine code so that a computer can execute. So, this process is divided into several key phases. First is lexical analysis. This is the first phase where the source code is broken down into tokens, the smallest units of meaning in programming. Second, we have syntax analysis. Here, the tokens are analyzed to check whether they follow the grammatical structure of the programming language. Then we have semantic analysis. This phase ensures the code is meaningful, verifying that operations and types align logically. Then we have intermediate code generation. An intermediate representation of the code is created, which is easier for the compiler to optimize and translate into machine code. Then the intermediate code is optimized to improve performance and reduce resource usage. Then finally, the optimized code is translated into machine language, which is ready for execution. So today we'll focus on the first two phases, lexical analysis and syntax analysis, as they form the foundation for all subsequent steps. These phases help ensure that the source code is valid and well structured before moving forward. Okay, now let's take a closer look at lexical analysis, the first phase of the compilation process. So, lexical analysis is the process of breaking the input program written as a stream of characters into meaningful units called tokens. So tokens represent the building blocks of a program, such as keywords, identifiers, operators, and literals. The input to this phase is the source code, which is essentially a continuous stream of characters without structure. And the output is a sequence of tokens For instance, if the input code is integer x equal to 10, the tokens generated would be integer x equal to 10, 4 tokens, where we have keyword, identifier, operator, and literal, 4 tokens. So the lexical analyzer not only tokenizes the input but also removes irrelevant details like white space and commands. For example, if the source code includes a comment, it will be ignored during this phase. So this step ensures that the code is clean, organized, and ready for the next stage. Without proper lexical analysis, the compiler would struggle to interpret the program effectively. Okay, now we'll try to understand the concept of tokens, patterns, and lexemes, which is essential for grasping how lexical analysis works. So, a token is a category or type that represents a group of similar lexemes. For example, tokens include identifiers, keywords, operators, and literals. They act as labels for the smallest meaningful units in code. Second, we have lexeme. So, a lexeme is an actual instance of a token. For example, in the line of code where we have integer x equal to 10, integer and x are lexemes that correspond to the tokens, keyword, and identifier respectively. Pattern. Pattern is it defines the structure of a token. It provides the rule or regular expression used to identify lexemes for a specific token type. Um, for example, the pattern for an integer literal might be a sequence of digits. So, by combining these three components, a lexical analyzer can efficiently recognize and categorize parts of the source code. For example, if it matches a lexeme like X to the identifier token by checking it if adheres to the pattern for identifiers. So we'll also see an example here now. Okay, so the lexical analyzer plays a vital role in the compilation process, acting as the first phase where raw source code is transformed into tokens. So first of all, it removes white spaces and comments. Um, the lexical analysis eliminates unnecessary spaces and comments, ensuring the source code is clean and ready for analysis without um, any extra elements. Then its primary job is to scan the code and recognize the meaningful tokens like keyword, operators, literals, and identifiers. So, so these tokens are then passed on to the syntax analyzer. Third, it detects and handles lexical errors such as unrecognized characters or invalid tokens, ensuring that these issues are flagged early in the compilation process. And then lastly, it interacts with the symbol table. Um, it interacts with the symbol table to store and retrieve information about identifiers such as variable names and their attributes. So, by performing these tasks, the lexical analyzer sets the stage for the subsequent phases of compilation, ensuring the input is well structured and error free before further processing. Okay, now regular expressions in lexical analysis. So, regular expressions or regex, these are crucial tool in lexical analysis. They define the patterns that help identify and classify tokens in the source code. So, first, these regular expressions are employed to match and recognize specific types of tokens like identifiers, numbers, keywords, and operators. This enables the lexical analyzer to process the input systematically. Um, for example, if you look at this identifier, the pattern A minus Z, A minus Z, this is the pattern which matches variable names or function names in programming languages. For example, my var one or temp, it would be match this pattern. So next we have integer. If you look at the pattern 0 to 9, then plus, which matches numerical literals composed of one or more digits such as 42 or 123. Then keyword, which is a predefined set of words such as integer, float, or return, which matches specific reserved words in the programming language. So regular expressions are incredibly efficient because they allow for precise and flexible token matching, even in complex scenarios. For example, they can distinguish between valid identifiers and keywords or ensure numbers adhere to the correct format. So, understanding and writing regex is a critical skill, not just in lexical analysis but also in other areas like data validation and text processing. Okay, now let's take a look at a practical example of how a lexical analyzer tokenizes an expression. Consider the line of code here where we have a equal to b plus 42. Now when processed, the lexical analyzer breaks this expression into the following tokens. First we have identifier. A and B are classified as identifiers. These represent variables that can store values and are user defined. Second, we have operators. So equals and plus, these are two operators. The assignment, this equal sign is the assignment operator and plus is the addition operator. Third, we have literal. 42 is identified as a literal because it is a fixed numeric value. Then fourth, we have delimiter. The semicolon acts as a delimiter, marking the end of the statement. Now each token is categorized based on its role in the expression, ensuring that the program structure is well defined and easy for the compiler to interpret. This breakdown is essential for the compiler to understand the meaning of the statement and translate it correctly into machine instructions. And this example illustrates the efficiency of lexical analysis in recognizing and organizing code components systematically. Okay, now let's move forward to syntax analysis. Now that we have covered tokenization, we'll now go to next critical phase in the compilation process, which is syntax analysis. Now, syntax analysis, also called parsing, it is the process of analyzing the sequence of tokens produced by the lexical analyzer. It checks whether these tokens conform to the rules of a formal grammar defined by the programming language. In simple terms, we can say it ensures the structure of the code is correct. Now, the input to this phase is the list of tokens generated by the lexical analyzer. For example, in the statement a equal to b plus 42, the tokens are a equal b plus 42 and semicolon. These are the tokens that is been created by using the lexical analyzer, and now these are analyzed for structural correctness. Then the output of syntax analysis is typically a parse tree or an abstract syntax tree. These trees represent the hierarchical structure of the code. The AST simplifies the parse tree by focusing on the meaningful elements of the program, omitting redundant grammar rules. Now, syntax analysis helps the compiler understand the logical structure of the code. If there is a syntax error, such as missing a semicolon or a misused operator, it will be flagged at this stage, and which will prevent the code from moving forward in the compilation process. So this phase bridges the gap between raw tokens and meaningful program logic, ensuring the code can be executed successfully once it's free of structural errors. Now let's dive deeper into the concepts of grammar and parse trees, which are essential for understanding how syntax analysis works. Um, grammar um, grammar is basically defines the syntax of a programming language using production rules. These rules specify how statements and expressions in the language should be structured. For instance, a rule like S belongs to A as B means that an S can be replaced by A followed by another S and then B. So grammars help ensure the language syntax is consistent and interpretable. We'll also see some examples in our next slide. Now, parse tree. A parse tree is a visual representation uh, of the derivation of a string based on the grammar. It shows how the rules are applied to form valid expressions. For example, in the expression a plus b, the parse tree will have a root node for the operator plus, and two child node for the identifiers a and b. Now, the parse tree helps the compiler understand the hierarchical structure of the code, which is crucial for tasks like type checking and code generation. And by combining grammar and parse trees, syntax analysis ensures that every piece of code adheres to the programming language rule, avoiding ambiguity and errors in program execution. Okay, now let's look at an example of grammar which is essential for defining the syntax of a programming language. Here we have a set of grammar rules. First, we have pointing to E. This means the starting symbol S can be replaced by the non-terminal symbol E. Every derivation will begin with this rule. Second, we have E pointing to E plus T or T. This indicates that E can either expand into another E followed by a plus and a T, or directly into T. Now, this rule allows for constructing expressions involving addition. Then third one is T pointing ID or num. Now this defines T as either an identifier ID or a number num. For example, ID could represent a variable name like X, and num could represent a numeric value like 42. How it works? So using these rules, we can generate expressions like x plus y or 5 plus 10. For instance, if we start with S pointing E, then apply the second one, and then finally the third one, this step-by-step expansion process forms the backbone of syntax analysis, where the compiler verifies that an expression adheres to these rules, and it ensures that the code is grammatically valid, setting the stage for further processing. Okay, now here let's see how an expression is parsed using a parse tree. For this example, we are parsing the expression a plus b. Now, using the grammar rules we discussed earlier, the parse tree is constructed as follows. Now, the root of the tree is E expression, representing the overall structure of the expression. The rule E pointing to E plus T is applied here, the first one. So the tree branches into E, the plus operator, and T. So we have E, and then it branches into E, the plus operator, and T. Then the rule of E pointing to T is applied to replace the left E with T. Now if we replace the left E with T, then both T nodes are further broken down using the rule T pointing to ID, and then now we are representing the identifier A plus B. Now if you see here, we are changing the right T on the second expression, the right T, we are changing it to ID, and then now we have on the third line we have T and ID, and then the operator plus is at the center of the structure, and then A and B are at the leaf nodes representing the operands. Now this hierarchical structure captures the grammar of the expression, ensuring it adheres to the programming language's rules. The parse tree is crucial for the compiler to understand how the components of the expression interact, laying the foundation for semantic analysis and code generation. Okay, now let's discuss the types of parsers, which are essential components of the syntax analysis phase in a compiler. Parsers are classified into two main categories based on their approach to analyzing the grammar. First is top-down parsing and then bottom-up parsing. On the first one, the parser starts at the root of the parse tree and works its way down to the leaves, following the production rules. Then some common examples of top-down parser includes a recursive descent parser and predictive parser. So the first first parser uses a set of recursive functions to process the input. It is straightforward to implement but may struggle with left recursive grammars. Then the second one, LL parser. This is a more advanced type of top-down parser that avoids recursion by using a look-ahead mechanism. It's suitable for a restricted class of grammars known as LL grammars. Then on bottom-up parsing, which starts from the leaves like tokens. It starts from the tokens and works upward to construct the parse tree. So some common examples are shift reduce parser, which shifts input symbols onto a stack and reduces them based on production rules to form the tree. Then second is LR parsers. These are highly efficient and handle a wide range of grammars, which has some subtypes which include SLR, simple error. It is simpler but less powerful version of LR parsers. Second is LALR, look ahead LR, which combines the simplicity of SLR with the power of canonical LR parser. Then third one is canonical, the most powerful type, and it is capable of handling all context-free grammars. Now, the top-down parsers are intuitive and simpler to implement but are limited to specific grammar types, where bottom-up parsers, while more complex, can handle a broader range of grammars and are commonly used in modern compilers. And understanding these types of parsers is essential for selecting the appropriate parsing strategy based on the grammar of the programming language being implemented. Okay, now let's explore a practical example of top-down parsing using the provided grammar and input string. Now the goal is to derive the string ABB step by step. So the grammar rules are, first one is S pointing to A as B, then second is S pointing to E, where E represents the empty string. Now the input string to parse is AABB. Now on step 1, we'll start with the initial symbol S and apply the rule S pointing to A as B. Now the string is partially derived as A as B. On step 2, for the new S in the middle, apply S pointing to A as B again. The string becomes AA as BB. Then on final step, We'll replace S with E using the second rule, and this simplifies the string to AABB, which matches the input. So this step-by-step derivation constructs the parse tree from the root S down to the terminals A, B, and the empty string adhering to the grammar rule. Now, the top-down parsing works by expanding the grammar rules from the root toward the leaves, ensuring each step follows the grammar precisely. It's simple and intuitive, but can struggle with left recursive grammars, which this example avoids. So by following this derivation, we ensure that the input conforms to the grammar, highlighting how top-down parsing validates syntactic correctness. Let's now explore how bottom-up parsing works. The goal is to parse the expression a plus b and construct its parse tree step by step using the provided grammar. So first we have E pointing to E plus T, second is E pointing to T, third is T pointing to ID. So the input string is A plus B, and the parsing process proceeds as follows. Like on step 1 we have shift A. The parser reads the first token A and places it on the stack. Then on step 2 it reduces ID pointing to T. So according to the rule T pointing to ID, the identifier A is reduced to T. Now the stack contains T. Then on third step, shift plus means the parser reads the next token plus and pushes it onto the stack. The stack now contains T plus. Then on fourth step, shift B, the parser reads the next token B and places it back on the stack. The stack now contains T plus ID. On step 5, reduce ID pointing to T. Using the rule T pointing to ID, B is reduced to T. The stack now contains T plus T. And then finally, using the rule E pointing to E plus T, the entire stack is reduced to E, representing the parsed expression. Now, the bottom-up parsing constructs the parse tree from the leaves, which is tokens, upward to the root, applying reduction rules at each step. It is more robust than top-down parsing and can handle a wider range of grammars, making it a preferred choice for many modern compilers. Okay, now let's see the abstract syntax tree, which is an essential concept in the parsing process. Now, what is an AST? AST is an abstract syntax tree, which is a simplified representation of a parse tree. While a parse tree captures every detail of the grammar, an AST focuses only on the structure of the expression and its meaningful elements, eliminating unnecessary syntactic details. So it abstracts away grammar rules, keeping only the core structure needed for further processing, and it provides a compact hierarchical representation that is easier for the compiler to analyze and manipulate. Now let's see this example here. We have the mathematical expression a plus b multiplies c, and its AST looks like this. So first we have the root node, which is plus, which represents the addition operation. Then the left child a is the first operand of plus. The right child multiplication represents the multiplication operation, and which is evaluated first. So we will evaluate the multiplication operation first, and that will be on the right side, right child. The children of multiplication, the children of star B and C are the operands of the multiplication. So uh, if you look at the expression, so B and C are the children of the star, which is the operand of multiplication, and then A is an operand of plus, so which is the root, and which is on A is the left child and the star is the right child. So this is how we can have a abstract syntax tree from this mathematical expression. Now the AST simplifies the code structure and making it easier for semantic analysis by checking for type correctness or variable scope, and then it also do code optimization by transforming the structure to improve efficiency. Then it converts the structure into machine readable instruction. So by focusing on the essential elements, the AST becomes a cornerstone in the compilation process, bridging the gap between syntactic analysis and execution. Okay, now let's focus on an important aspect of parsing, which is error handling. Errors in parsing occur when the input code doesn't conform to the rules of the language, and they can generally be categorized into two types. First is lexical errors and syntax errors. So, on lexical errors, these errors arise during lexical analysis and are typically caused by invalid tokens. For example, if an illegal character or symbol is used in the source code, such as at in a variable name, the lexical analyzer will flag it as a lexical error. Then, syntax error. These occur during syntax analysis when token sequences are unexpected or um, uh, violate the grammar rules. For instance, the structure of the code may not align with the expected syntax. Here, if you consider the input integer 5x, here the error is that a variable name cannot start with a digit. The parser will definitely identify this as a syntax error, since the grammar rule for identifiers expect them to begin with a letter or underscore. So the goal of error handling in parsing is to detect, identify the location and type of error accurately, and then provide clear feedback to the programmer about what went wrong. So it report to the programmer. Then it will attempt to continue parsing the rest of the code wherever possible using techniques like panic mode recovery, phrase level recovery. Well, in panic mode recovery, we it just skipping input until designated synchronizing token is found. So this is how it recover. And then on phrase level recovery, it can be done by replacing erroneous constructs with a valid alternatives to continue parsing. Now, why it matters? Well, it is effective. It is a effective error handling, which ensures that the compiler can give meaningful feedback to the programmer, which enable them to correct errors efficiently and improve code quality. So, by handling errors systematically, parsing ensures that even faulty code can be analyzed to some extent, making the debugging process more manageable. Okay, now let's see some tools of lexical analysis which automate the process of generating lexical analyzers, saving both time and effort for developers. So Lex is one of the most widely used tools for this purpose, and it is a program designed to generate lexical analyzers based on patterns provided by the user. These patterns are defined using regular expressions and are associated with specific actions to be performed when the pattern is matched. So here we have an example. So if you look at this example, this is the structure of the Lex program is like we will have a definition section where we will have this modulus, and then curly braces, and then it will finish, it will close the modulus and curly braces and parentheses. This is the definition section. This is where you include necessary headers such as studio, stdio.h for printing results. So this is the definition section. And then second, we have a rules section. So it will have here you define patterns and associate them with actions. For example, you have a pattern here. So the pattern here we have a minus z. So this line is the pattern which matches identifiers and triggers the action printf identifier. So the pattern 0 to 9 plus matches numbers and triggers printf number. So how it works? So when you run this program, it reads the input and matches identifiers to the first pattern, printing identifier. Also it matches numbers to the second pattern, printing number. So this is how it works. So tools like Lex make it easy to handle complex pattern matching using regular expressions, and it reduces manual effort in writing lexical analyzers from scratch. Then it also ensures consistent and error-free tokenization of source code. So by using tools like Lex, developers can focus more on higher level aspects of compiler design while automating repetitive tasks like token recognition. So here we have another tool for syntax analysis which automate the process of generating parsers. Two widely used tools for this purpose are YACC and Bison. So YACC is yet another compiler. That means yet another compiler, YACC. And its improved version is Bison, which are tools used to generate parsers based on a given grammar. Now these tools take grammar rules as input and generate code for a parser that can analyze and validate the structure of input strings. Now here is an example of a Bison program for recognizing simple arithmetic expression. Here if you see we have a grammar rule here. Now we have a definition section first where we have the required headers, stdio for output. So and the next section is rules section where we have we contains grammar rules here. So we have e plus t, which defines that an expression e can consist of another e followed by plus and a term t. Then TID, which defines that a term t can be an identifier. Then we have action section. For each rule, specific actions are defined. For example, when the rule E plus T is matched, the program prints addition. So how it works? The tool processes the grammar and generates a parser. When this parser runs, it matches the input against the defined rules. And if the input conforms, it triggers the corresponding actions and printing addition for A plus B. So, syntax analysis tools are important because they simplify parser generation, especially for complex grammars, and they ensure error-free syntax analysis by automating rule application. They also allow developers to focus on high-level grammar design rather than low-level implementation. And tools like YACC and Bison are widely used in compiler construction and help bridge the gap between grammar definitions and practical parsing solutions. So now let's see how Lex and YACC are often used together in compiler design. These tools complement each other to handle both lexical analysis and syntax analysis seamlessly. Now, why use Lex and YACC together? Because Lex is used for token definitions, it scans the input, matches patterns using regular expressions, and generates tokens that represent keyword, identifiers, operator, and more. And then YACC is used for defining grammar rules, and it processes the tokens generated by Lex to analyze the structure and build a parse tree. Then so basically Lex generates the tokens and passes them to YACC, and then YACC applies grammar rules to parse the input and triggers the associated action. So so there are some benefits of combining Lex and YACC because Lex handles low level details of scanning and tokenizing, and YACC focuses on high level syntactic structures. It automates the tedious process of writing a lexer and parser manually, and it supports complex grammars and patterns for various programming languages. So, by combining these tools, developers can efficiently implement both lexical and syntax analysis for compiler design. So, we'll see now some practical applications. These processes are fundamental in many areas of software development and programming tools. So, first, we already know compilers, which include lexical and syntax analysis, which are the first two phases of a compiler. They translate source code written in a high level language into machine code by breaking down the input into tokens and ensuring the tokens are structured according to the grammar rules. Now, without these steps, compilers would be unable to validate or transform source code into executable instructions. Then, interpreters execute source code line by line. They use lexical and syntax analysis to identify tokens and validate the syntax before executing each line. For example, Python interpreters analyze the structure of a statement like x equal to 5 plus 3 before calculating the result. Then, static analysis tool. These tools analyze code without executing it, helping developers identify errors, enforce coding standards, and optimize performance. So lexical and syntax analysis enable these tools to detect issues like unused variables, incorrect syntax, or uninitialized variable. And it also provides real-time feedback to developers in integrated development environments. So basically these two provide the foundation for ensuring code correctness, performance optimization, and usability in compilers, interpreters, and static analysis tools. So, to connect the concept of lexical and syntax analysis to a real world application, let's look at a JSON parser, a tool widely used in web development to process and validate JSON data. Now, the first step in parsing JSON is lexical analysis, where the parser identifies tokens from the raw JSON string. For example, in the JSON string like name, John, age, 30, tokens include like and then like the brackets, curly braces, or the braces or parentheses. These are the tokens like colons, comma, name, age. These are keys, and then some values. These are tokens which is identified by the lexical analysis, and then these tokens are extracted by recognizing patterns as string, numbers, or punctuations. And then once tokens are identified, syntax analysis ensure the JSON structure adheres to the JSON grammar rule. So basically JSON objects must start and end with curly braces. So keys must be strings enclosed in double quotes, and key value pairs must be separated by colons, and multiple pairs are separated by commas. I will include this example. I will add this example in Moodle, so you will have a better idea. So while lexical and syntax analysis are foundational in compiler design, but they also come with their own set of challenges. So first of all, we can have a challenge to handling ambiguous grammars. Like ambiguities arises when a single input can be interpreted in multiple ways based on the grammar. Resolving ambiguity often requires adding precedence and associatively rules, which can complicate grammar design. Then optimizing performance, like efficient parsing is critical, especially for large programs. So lexical analyzers need to tokenize inputs quickly, while parsers must minimize the time complexity of checking syntax. And balancing speed and accuracy is constant challenge. Third is managing large grammars for complex languages. Well, modern programming languages like Java or Python have extensive and intricate grammars. Like handling such large grammars require careful modularization of grammar rules and tools like Lex and YSEC to simplify the parsing process. So the complexity increases as languages evolve with new features and require continuous updates to the grammar. Here we have two tasks for you. First one, we have a code and you will identify the tokens and their types. And then second one is parse tree. From using these grammar rules, and we have an input and you will draw the parse tree. So these two is a class work, will be graded, and you have that in module that you will submit it in a PDF file. Only PDF file is accepted. So you will have the first task, and then you will have the tokenization, and then next you will draw the parse tree. So in a simple way, in 1 page or 2 page, whatever it is, you will submit this task by this week, same week. So, and there will be 5 points for that, and that will be counted as class work or class lab. And then, so that's all for now. You can check some documentation online, or I will also try to add some resources, and I'll add the examples for the JSON parser and some other slides. And if you have any questions, please let me know. Thank you.